The first official images from the Vera C. Rubin Observatory have now been released, marking a major milestone in modern astronomy. Located atop Cerro Pachón in Chile's Atacama Desert, the facility has begun limited operations ahead of its full scientific launch expected in late 2025. Its primary instrument, the Simonyi Survey Telescope, is now paired with the largest digital camera ever constructed, capturing images at 3.2 gigapixel resolution per exposure. The scale of this data is substantial. A single image from the Rubin Observatory would require approximately 385 4K televisions placed side by side to be viewed at full native resolution. During operations, the observatory is projected to collect around 20 terabytes of data every night, all transmitted through a dedicated 100-bit fiber linked to data centers in the United States for immediate processing. The first imaging campaign was conducted over just 10 hours of test observations. Despite its limited duration, it detected millions of stars and galaxies alongside thousands of asteroids, 7 of which were classified as near-Earth objects. The observatory's most publicly shared early output is a mosaic informally referred to as the cosmic treasure chest. This single image was produced using 1,185 exposures captured over 7 nights, covering 25 square degrees within the southern Virgo cluster, approximately 55 million light-years away. The dataset contains over 10 million resolved galaxies, representing just 0.05% of the 20 billion galaxies the Rubin Observatory is expected to catalog over its 10-year primary survey. A separate mosaic focused on the Lagoon Nebula region demonstrates the facility's ability to merge wide-field observation with high sensitivity. While the Hubble Space Telescope captured this region at a narrow zoom covering only around 4 light-years across, the Rubin Observatory imaged the entire 55 by 20 light-year structure within a single compiled frame. The mosaic also resolves surrounding objects, including Messier 21, Messier 20, Trifid Nebula, Bochum 14, and NGC 6544, each visible with clear photometric differentiation across ultraviolet, visible, and infrared wavelengths. The color data is algorithmically assigned. Infrared wavelengths are represented as red, ultraviolet wavelengths as blue, ensuring scientific accuracy rather than artistic enhancement. Unlike targeted observatories such as Hubble or James Webb, which focus on single objects for deep analysis, the Rubin Observatory operates as a wide-field time-domain survey system. Its field of view spans 10 square degrees per exposure, equivalent to about 45 full moons, allowing it to scan the entire southern sky every 3 nights. Over time, these repeated observations will form a searchable motion dataset. This capability is expected to produce the largest catalog of solar system objects ever assembled, potentially identifying millions of previously undetected asteroids within just the first 2 years. The observatory has been meticulously designed to pursue 4 major scientific goals with exceptional precision. First, it focuses on unraveling the mysteries of the universe's composition by mapping the distribution of dark matter and dark energy through large-scale gravitational lensing observations. This allows scientists to trace how invisible forces shape the structure and expansion of the cosmos. In addition to its cosmological mission, the observatory plays a crucial role in planetary defense by identifying and cataloging solar system objects, ranging from main-belt asteroids to potentially hazardous near-Earth objects, and even rare interstellar visitors passing through our neighborhood. Its high-cadence monitoring also enables rapid detection of transient astronomical events, such as supernovae, gamma-ray bursts, and sudden fluctuations in stellar brightness, providing valuable real-time insights into some of the most energetic and short-lived phenomena in the universe. Lastly, the observatory contributes to a deeper understanding of our own galaxy by constructing an exceptionally refined stellar map of the Milky Way, charting populations within the halo and outer disk to reveal the evolutionary history and structure of our galactic home. During its first test run, it recorded 46 RR Lyrae variable stars, a class of pulsating stars used as distance markers in galactic surveys. Projections estimate that Rubin will eventually identify over 100,000 of these distance indicators across halo regions stretching beyond 1 million light-years from Earth. These detections will allow researchers to refine three-dimensional models of the Milky Way's outer structure, including tidal streams and dwarf galaxy remnants. Operational design is modular and automated. The Legacy Survey of Space and Time (LSSD) camera is fitted with 189 individual CMOS sensors, each cooled via active thermal regulation. 3 fused silica lenses, including a 1.6-meter wide front element, ensure consistent clarity across the entire focal plane. A robotic filter wheel allows rapid switching between photometric bands without interrupting exposure cycles. Each exposure is time-stamped and logged into a dynamic event database where automated classifiers identify motion, luminosity changes, and spectral anomalies. These pipelines enable near real-time alerts for transient phenomena, which can be forwarded to partner observatories for immediate follow-up. Total storage requirements over the 10-year survey are projected to exceed 500 petabytes, comparable to aggregating every image ever posted on major social media platforms over a decade. Dedicated software infrastructure is under construction to manage archival access, public data release, and automated mining through machine learning classification systems. Unlike some previous surveys with delayed access, Rubin's policy allows regular public image releases throughout operations rather than waiting until survey completion. Although the Rubin Observatory is not operated by NASA or ESA, but rather funded by the U.S. National Science Foundation and Department of Energy, it is already positioned to function as a core component of international observation networks. Its latitude in the southern hemisphere also complements the sky coverage gaps of northern facilities. In many operational scenarios, Rubin will serve as the detection instrument, while observatories such as James Webb or the Giant Magellan Telescope will act as characterization platforms, allowing precise study of objects first identified by Rubin's wide-angle sweeps. The observatory is named after Dr. Vera Rubin, whose measurements of galaxy rotation curves provided the first empirical evidence supporting the existence of dark matter. The naming is considered appropriate by many in the scientific community, as the facility is expected to play a direct role in quantifying dark matter distribution via gravitational lensing signatures across billions of galaxies. Final system validation is scheduled to complete by late 2025. Once activated for continuous operation, the telescope will scan the sky every night for approximately a decade without scheduled seasonal pauses, with automated weather-based override protocols redirecting observational targets based on atmospheric stability and seeing conditions. Its location within the Atacama Desert, one of the driest and clearest regions on Earth, affords over 300 usable nights per year, maximizing survey efficiency. Early scientific results confirm that wide-area, high-frequency monitoring is capable of revealing data that would otherwise be invisible to conventional telescopes limited to targeted fields of view. Even within its provisional dataset, Rubin has already identified asteroidal trajectories, variable stars, and galaxy clusters undergoing interaction processes previously uncatalogued. None of these results represent the system operating at full sensitivity. Analysts expect exponential increases in detection volume once filter cycling, automated orbital prediction software, and external cross-referencing networks are fully engaged. For the general public, the primary takeaway from these first images is scale. The 10 million galaxies seen in one image do not represent a special or rare region of space. They represent average galactic density at that scale. This is merely a 0.05% preview of the 20 billion the system is scheduled to document. As the survey progresses, astronomers expect to identify objects never before seen in time-space mapping, including long-period comets, free-floating rogue planets, rare supernova precursors, and potentially even optical signatures of interstellar objects before they enter the inner solar system. The first images do not represent the peak of what the observatory can do. They represent the baseline. With full commissioning still pending, every subsequent release will contain progressively higher quality data. The Rubin Observatory is not designed for one-off discoveries, but for pattern detection at a scale that has never been attempted in astronomy. For the first time, it will be possible to rewind and fast-forward cosmological scale datasets with frame-by-frame documentation of stellar and galactic evolution in real time. More images will be released in staged intervals throughout 2025 and 2026 as calibration improves. They will continue to expand in coverage until the entire southern sky is logged into a continuous historical archive. For researchers, this represents a new model, astronomy, not as isolated snapshots, but as a complete surveillance record of the universe in motion. If you found this breakdown informative and want to stay updated as more discoveries come in, make sure to leave your thoughts in the comments. And if you'd like to see more deep dives like this, don't forget to like the video, subscribe to the channel, and turn on notifications so you never miss an update. Thanks for watching.